I am working for Huawei on the Bison compiler project. Yeah, today I want to talk about the improvements what we did in the LLVM compiler to accelerate the matrix operation on the ARM SVE target. Yeah, so the matrix type was first introduced in this PR by Florian, and its purpose is to provide a source code level solution to write high-performance code for matrix operations. And it also provides very user-friendly interfaces. As you can see, with a simple multiply operator, the complicated loop can be eliminated. And what's more, after lowering the matrix type to the internal intrinsic, the compiler can easily generate the optimal vector instructions. Yeah, but the Clang matrix type support is still an experimental feature, so it has some limitations. For example, it supports only the small matrix size because of some limitation in the compiler backend. And ARM SME provides matrix registers, and it also provides some matrix instructions. So this can be naturally used to support the Clang matrix type. Let's see an example. The source code is trying to multiply two matrices. Each matrix has 16 double values. So with current Clang implementation, the first matrix was split to two sub-matrices, and it requires 32 FMO or FMA related instructions for the big matrix multiply. But with SME, with the outer product instructions and the bigger vector register, assuming the SVE vector base is 256, we only need 4 outer product instructions for the matrix multiply. I think this is a big improvement. So to support the SME lowering for the Clang matrix type, we can base on the existing lower matrix intrinsic path in the LLVM. At the first step, the lower matrix intrinsic, we try to propagate the matrix shape info based on the matrix intrinsic. So for this case, after the matrix shape propagation, we can conclude that the matrix add is for 4-4 matrix, and all the other rows are also for the 4-4 matrix. So we don't need to change anything here. I think the current logic is enough for us. And for the second step, the lower matrix intrinsic path will try to lower the matrix intrinsic. We need some change here to avoid manually maintain the JL register state. We emit a call. The SME matmore float 8. We emit a call to a new developed SME library for the matrix intrinsic lowering. And we also add some optimization here to optimize the memory access. As you can see, the SME library calls are designed to take the matrix pointer as parameters. So we directly pass the matrix pointer %0 and %1. Yeah. So at the last step, the lowering path, we try to lower the other matrix operations like the matrix add and the matrix out or something like that. For this case, we lower the matrix add to an external function call, which is also defined in the SME library we talked earlier. In the external function call, the SVE instruction will be used instead of the original neon instructions. But this external function call is not a must-have. We can just inline the SVE lowering in the lowering path. Okay, this is my final slide. We also consider another solution for the SME lowering. It is not based on the existing lower matrix intrinsic path. It is in the Clang frontend. Because it has some advantage, right? It can, with this solution, the SME library can be easily switched to another one, and it may be easily to implement the solution by itself, and it can also be possible. Okay, it can also be possible to support a large matrix because we should be able to make the matrix type be returned and passed as pointers in the Clang frontend. It also has some disadvantages. The largest one is it introduces big function call cost, especially for the SME, the register handling. That is all my sharing. Thank you very much.